In this video, we're going to introduce a new concept of critical points, but it'll be related to the absolute max and absolute min we talked about in the previous video. All right, so first we're going to talk about these things called local max and min. So in the previous video, we talked about absolute, that's just the biggest y value of the entire function, absolute minimum, the lowest y value of the entire function. But now we're going to talk about these local max and min. So a local maximum means my output value, my y value, is the largest of everything around that thing. All right, we'll look at an example in a second to see what we mean by around. All right, that's something that's defined more precisely in upper level math classes, but for us, we're just kind of looking near that value. Is it the biggest one? All right, a local minimum, you can imagine, same thing. Our y value is the least for everything around that value. So here we're not looking at the entire function all at once. We're just looking at small pieces of the function. All right, so let's look at this graph and identify all the local extrema. So extrema is the word for maxes and mins because they're the extreme values. All right, so where are these things going to happen? All right, so first let me just say, like, say I thought this was an absolute maximum. All right, if that dot there was an absolute maximum, it should be bigger than everything around it. But if we think about the stuff that's just around it, there's a bunch of other values that are bigger than it right there. All right, so that's not an absolute max because there's some y values close to it that are bigger. It's also not an absolute min because there's some y values close to it that are smaller. Right. So what are our local extrema going to be? Well, the first time we're going to get one local extrema is down here, and that's going to be a local minimum. Because if I think about this specific point right at the bottom of this valley, if I think about any y values close to it, so again, I can just kind of think about like a little box around here, any of the y values close to it are above it. Right, so anything in that little green box, all those y values are higher than that black dot, which means that's a local min. All right, this graph is symmetric, so you can probably imagine that this dot over here is also going to be a local min, because everything else near it, if we kind of just think about a little green box, that is going to be greater than it. And then here and here, these are going to be local maximums. Yeah, because if I think about little dots or little boxes around these things, everything in those boxes, the y value is going to be less than, lower than those black dots. We have one final local extrema, and that's going to be this here, right in the middle, because anything compared to that dot is when we start increasing our y values, and that's the lowest. So this one is a local min. As you can see, the definition might be a little confusing, but the basic idea is a local max or local min. The local mins are the bottoms of any valley in your graph, and the local max are the tops of any hills in your graph. All right, so those are local extrema. There can be a lot of local extrema because every single hill and valley gives you a local extrema. But there can only be one absolute max or min because that's the whole function we're looking at once. What's the biggest y value? All right, so I'll write it down. It can be lots of local extrema. There can be only one absolute extrema. All right, so now we talk about what a critical point is. All right, these are something that come up a lot in this unit. So a critical point is anywhere where our derivative is equal to 0, because that's important stuff to know, or when the derivative does not exist. All right, so both of those are kind of the extreme values. All right, something important happens when the derivative is 0. Also, something weird will probably happen when the derivative does not exist. All right, so these are critical points because they're where the interesting things are going to happen for our original function. All right, why are critical points important? All right, because every local max or min occurs at a critical point. So I thought about this graph. Everywhere my tangent line is flat, that can be the bottom of a hill or peak of a valley, and we know those are local extrema. But also where my derivative does not exist, I can have these sharp corners, or there can also be local maxes and mins. All right, so those are the only places where they can happen. All right, either a horizontal tangent or something interesting can happen when the derivative does not exist. So, all right, so critical points are important because they're where maxes and mins occur. All right, so now we're going to look at the strategy of finding an absolute max and min for a function. So if we think about what this function could look like, again, let's just draw some random function. And say this is the start and this is the end. All right, there's two places where an absolute max or min can occur. The first place is they can happen at any of our local extrema. And if we look at this one, all right, we identify where the local extrema are, and then the biggest one is going to be our absolute max. All right, but for our absolute min, this is the only local min, but it's actually not the absolute minimum because that happens here. All right, that point's a little bit lower. This is our absolute minimum. All right. So absolute extrema occur at local maxes and mins, and we know those happen at critical points. All right. And that's the reason a lot of people will get this question wrong. They'll just focus on that one, but there's one other place that can happen, or the endpoints of the interval. All right, so those are the two places our absolute extrema can happen. So when we're doing this, the first thing we'll do is find critical points. All right. And again, critical points, we take the derivative, so f prime of x is equal to 2x plus 0. All right, we see if it's undefined, 2x is never going to be undefined, and we see when it's equal to 0. All right, so our one critical point is 0. And now we find the values. So we have three values we have to try for this problem. All right, our x values we have to try are the endpoints, -1 and 4, and also any critical point. So in this case, critical point is 0. All right, and we were looking for the absolute max of f, so we're going to plug it into our original function, x squared plus 3. All right, so when I plug in -1, I get 4. When I plug in 0, I get 3. When I plug in 4, I get 16 plus 3 is 19. All right, so these are the only places where I know an absolute max or min can happen. So my minimum is going to be the smallest value. All right, so this is my absolute min, because 3 is the smallest y value you get out. And my absolute max happens at the biggest value. That's my absolute max. All right, so this is the strategy for finding absolute extrema. You identify the critical points, you plug those in, not forgetting you also have to do the endpoints, all right, like we did there. All right, so we'll do one more example. All right, find the absolute max and minimum of this function on the interval. So the first thing I'm gonna do is find the critical points. All right, and to do that, I have to take the derivative. All right, so f prime of x, it's gonna be 4. All right, the derivative of the square root of x is 1 over 2 squared of x. The derivative of x squared is 2x. All right, so if I simplify a bit, the 4 and the 2 are going to be 2 over the square root of x minus 2x. All right, so that is our derivative. All right, when is this going to be undefined? So this is does not exist. All right, in this case, it does not exist when x equals 0 because I can't put in a 0 on the bottom of that fraction. So that's one critical point, is when f prime of x equals 0. The other one is when this function equals 0. All right, so the way I would solve this, I'd probably add the 2x to the other side, multiply both sides by the square root of x, square everything to get rid of that square root, divide by 4, and then take the cube root, x equals 1. All right, so now I have 2 critical points, and now I can do the last part of my problem. I have to plug these in. So to plug in my endpoints, 0 and 4. I also have to plug in my critical points, zeros, an endpoint, and a critical point. I only have to plug it in once. I also have to plug in my other critical point 1. So I plug those in. 4 squared is 0 minus 0 squared is just going to be 0. 4 times the square root of 1 minus 1 squared is 3. 4 times the square root of 4. 4 times 2 is 8 minus 16 is negative 8. All right, so now I know my absolute max is the biggest value I get here. This is going to be my absolute max. Absolute min is the least value I see here, which is this. This is my absolute minimum. All right, so this is a useful thing that we'll have to use throughout this whole unit. All right, finding maxes and mins. I remember they happen in 2 places. They happen at our critical points, which is when our function does not exist, or our derivative does not exist, or our derivative is equal to 0. And we use those as well as the endpoints to figure out what my absolute max and absolute min are.